Hello and welcome to our first session of the Digital Days this year. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is GaN-SiC challenges for passive, EMC and power components. Our speaker is Andreas Nadler. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during this presentation. This means that you cannot ask questions during the presentation via microphone. But nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you can find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all of your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our speaker, Andreas, and I wish you an exciting presentation.
So, good morning, everybody. Hope everyone can hear me. Welcome to our first session, SiC-GaN challenges, especially for passive. So my name is Andreas Nadler. I'm field application engineer at Würth Elektronik eiSos. I'm sitting here in my home office in Bavaria, and I hope you enjoy. So what's our, I will share my screen with you. So exactly this one. Good, hope you can see the screen. All right, let's getting started. Well, our agenda, what are the, let's say, advantages of the wide bandgap devices? Why do we need isolated gate drive power supply, especially for high voltage designs where you usually use this wide bandgap devices? What kind of isolated topologies do we have? And which are the advantages or disadvantages? What are the main EMC issues in such designs? I will show you a layout example from, let's say, high power or let's say high frequency SiC and GaN design, which we made internally just for demonstration. And last but not least, we will take a look on what are the demands for a high current inductor for low voltage DC-DC GaN designs. So overview, why do we call it wide bandgap designs? Devices. Of course, we have a valence band and a conduction band. You maybe already heard from this from atomic structure in semiconductors. And we can see here silicium has a band gap of around 1.2 electron volts, and SiC and GaN are over 3 electron volts. This leads to a, let's say, high breakdown through voltage range, which leads to higher voltage level ratings of the devices, for example, over 1,700 volts for a SiC. And also has some another advantages. For example, for SiC, we have a very high thermal conductivity, which leads to a very good thermal performance, and we can get more easily rid of the heat of the devices. For GaN, it's not so so easy like with SiC. We have only 200 watt-meter per Kelvin, which leads to problems with the very small devices you can buy on the market for low voltage DC designs. You can buy their 1 by 1 millimeter MOSFETs of GaN, but the problem is really there to get rid of the heat very good. So it can be very challenging on such designs. Another challenge is driving SiC MOSFETs because of the slope of the gate drive voltage. So as you can see, the comparison between a silicium IGBTs and silicon carbide, we have a much more, let's say, lower slope this leads to let's say a voltage controlled resistor behavior, not like a lithium device, a voltage controlled current source. And therefore, it's very critical to use a very high gate voltage to switch on the device. You can see here an example calculation with a silicon carbide device. The maximum gate voltage of this device is plus 19 volt. And if you only use, for example, this is valid if you use it with a lithium MOSFET, you can use their 11 volt gate drive voltage to switch on the device. It's no problem, but with a lithium carbide, if you do not use the, let's say, full voltage swing of around 18 volts, you get very high losses because of the high drain source voltage, which you can easily have with these devices if you take a too low gate voltage. In this example, we have 2.6 volts drain source voltage multiplied by a current of 23 amps. You get 60 watt of losses at the device directly, and this is quite high, and it's very difficult to cool. And also from a, let's say, efficiency point of view, it's not quite nice. So it's very critical to drive the silicon carbide devices with very close to maximum gate voltage, as much as your application really allows you. So if you're talking about gate drive, we usually using in SiC or GaN devices or applications, which are mostly at the moment high voltage applications around 230 volts to 1000 volts in the main cases. We need isolated power gate drive supply voltage. So this auxiliary power supply here and an auxiliary which is isolated and a gate driver which is isolated. And why do we do this? Of course, we would like to protect maybe the front end user on the low voltage side here from electrical shock. Therefore, we need maybe basic or reinforced insulation depending on the system. We would like to protect the control unit, which is sitting here, the microcontroller and so on, all the measurement system. We would like to protect against EMI, of course. As we see later, we can get easily EMI problems with isolated the gate drive supplies in combination with fast switching SiC and GaN. And we can maybe easier control the high side FET if you have an isolated, dedicated driver for the high side. So there are main advantages to using, or main reasons to use isolated gate drive here. But there are some challenges, of course. First, you have to look what kind of voltage levels do we need to drive SiC and GaN. For GaN, usually 5 volt is the maximum, 6 volt the absolute maximum. Usually 5 volt you should not exceed. And usually you turn off with 0 volt or maximum minus 2 volts, depending on the manufacturer of the, let's say, GaN device. But you can see it's a very small window you have to switch or to turn on and turn off voltage. So, and these devices can be destroyed very easily. So you really have to take care to stay within these ranges. For SiC, depending on the manufacturer again, we have 15 to 20 volts turn-on voltage. And as you already heard, you should really go to the limit as much as your application allows you to get a very efficient, high efficiency switching. And for turn off, we usually use 0 to minus 5 volts to safely turn off the device. We also see later why. Critical in all gate drive systems is to get very low parasitic elements here. We see on the next slide. And to have a Kelvin connection on modern, let's say, lithium carbide MOSFETs from Cree and Infineon and so on, you find a dedicated source pin for only the Kelvin connection point. This Kelvin connection point you connect to your driver common mode ground. So which means usually here we have the plus 15 volts, for example, here minus 4 volts rail, and in the middle we have the 0 volts. And the 0 we connect directly on the very short path with the Kelvin point of the SiC or GaN FET. And as same we do with the driver, depending on the drive level system, you also connect the driver ground directly on a very short track and wide track to the Kelvin point. So we had really a single point, let's say, local power ground there. Okay, what's the current levels there, and what's the critical point there? Of course, if we switch on the device, we drive a current from the driver push-pull high side to the gate resistor, and to the, let's say, MOSFET, we charge up the internal capacitance, the Miller capacitance, and the gate to source capacitance. And we have a return current, which should be directly going back to the driver and to the auxiliary gate drive system. And if we turn off the device, we discharge the the Miller capacitance and the gate capacitance. Our second path, we can try to do this with let's say, a Schottky diode to, let's say, avoid turn off current going through this path. So we can choose different resistors here to control the turn on and turn off gate speed. And as we have always here very high di to dt levels, the problem is we should avoid any parasitic inductance in our system. Why? I think it's clear. Because every parasitic inductance we get from the layout, from components, from bad placement, whatever, we multiply this by the di to dt, and therefore we get a voltage, which can be a very high frequency kind of voltage. And therefore we get either problems with the turn on or turn off accidentally, or we get the problem with the EMI of the system, or we can easily destroy some other semiconductors if you have too high voltage ringing due to the, let's say, leakage inductance here in the system. So it's very critical to choose a very compact layout in this area here, not only in the high voltage area, which we switch the, let's say, really the power. More critical, let's say, the same critical path is also the gate drive path here on this side, on the high side and the low side of the half bridge. And if you have, of course, brushless motor or a three-phase engine, we have 3 of the stages here, and then we need 6 auxiliary power supplies and 6 isolated gate drive supplies. Another problem is the so-called Miller effect. You can see here, maybe this is the low side MOSFET in our half bridge, and if we turn on the high side or turn off the high side MOSFET, we drive a current through the Miller capacitance to the low side FET. And if we have the problem that, or if we have only 0 volt on the gate to switch off the device there, maybe we can exceed it with this voltage ringing due to the current we drive through the gate here on the low side. And maybe we can accidentally turn on the low side MOSFET, and therefore we get a short in our half bridge, or we get a loss in efficiency. If you use a lower voltage, for example, -5 volt or -4 volt, then we got more headroom to avoid this accidentally turn on, because you cannot avoid this completely. You always will see, usually in the most designs, some effect on when you switch the high side MOSFET and you take a look on the gate source voltage on the low side MOSFET. At the same time, you will see some effects there due to the Miller capacitance, because we got the current there. And as we cannot avoid this Miller capacitance, we have to make sure that the gate on the low side, for example, is really clamped pretty low, and we have no accidentally turn on there. Therefore, we need a dual rail auxiliary power supply in the most SiC lithium carbide designs. Another critical point from an EMI perspective or point of view is the isolation barrier. The gate drivers has an isolation barrier, and also our transformer, I show you later, has an isolation barrier or provides the isolation barrier, and every isolation barrier has some parasitic capacitance. And it's the most critical point in designing an auxiliary power supply for high voltage and high speed gate drive systems, to get this parasitic capacitance as low as possible. So a good point or a good value is under 10 picofarad. And with our design, we stay under 7 picofarad usually. So the lower the capacitance here, the lower the common mode current we, let's say, feed in the input of the system. So as we switch here with a very high dV to dt, we automatically, due to this, let's say, equation here, we have a common mode current flowing to the input of the system, for example. Therefore, we get EMI problems in our EMI measurements, and also maybe we can degrade the isolation barrier here. And also we can get some common mode ground bounds on the drive system, also get some disturbance in our control system. So it's very critical to get a very small capacitance in the isolation barrier. So what kind of topologies can we use in such, let's say, auxiliary gate drive supply systems? First, let's say, well known is push-pull. For example, from TI, there are many manufacturers which are doing these chips. So what's the advantage? It's a very cheap and fast solution, of course. It's only a 50% duty cycle rectangular generator here. So therefore, it's really cheap. But of course, as we have no feedback, no regulation, we have an unregulated output voltage, which cannot be accepted in some designs. In other designs, it can be accepted depending on your application. And therefore, as we have no regulated output, we need a very tight input voltage range. So, for example, 3.3 volt, 5 volt, 12 volt, there are many possibilities here. And as there are many different, let's say, fixed voltages, there are, let's say, hundreds of transformers which we can supply off the shelf with our, let's say, midcom partner. We have many different kind of isolation from functional, basic, supplementary, and reinforced insulation. As well, we get different kind of power levels and different kind of voltage levels here, which we can provide. So there are many transformers off the shelf. You do not have to design, let's say, a special design for you normally. There are always some regulations. Maybe we can, which are not fitting to the off-the-shelf transformer, but usually there are broad range already available. Another possibility is to use a flyback design. A flyback, we made a reference design for it coming from the Formula E. It was the origin of this design because they need a very, let's say, efficient, a very small and a very light solution in their cars. And every gram and every point of efficiency will help them. And every space they can save also helps them. Therefore, we made a standard product out of it with these two controllers. One is from Analog, one is from TI. So it's no opto feedback. So it regulates only by the reflected voltage from the secondary to the primary side. It's pretty nice. You will see later. Of course, it's a little bit more complex and expensive than the push-pull design, as we got a regulated IC here with selectable, let's say, switching voltage and so on. But you will get the regulated output voltages, and you have a wide input voltage range. So we have different kind of transformers, which helps you to cover 9 to 18 volts and 18 to 36 volts. So perfectly suited for 12 volt or 24 voltage rails. And of course, you can have multiple output voltage levels. For example, 2, 3, or 4, but the standard is 1 or dual output voltage for this design. So 20 volt and 0 volt, for example, or like in this picture, 15 volt and -4 volt. And of course, as I said, the power density is quite high. You will see the design is very compact and the transformer is very compact, but it can handle up to 6 watt. And we can also upgrade this with a little bit bigger core to 10 watt if required. So if you really need to drive, let's say, big silicon carbide or IGBT or GaN device with a very high total gate charge or with a very high frequency, as we did in the next slides with our demonstrator, you will need easily more than the standard 1 watt, which is quite common. So this could be a good solution for you. It provides you in a very small package. You can see, let's say, 1 cubic centimeter. It can handle up to 6 watt. It has 4 kV of dielectric insulation. We have only 6.8 picofarad coupling capacity, primary to secondary. And we have basic insulation for 800 volt of working voltage. So quite nice. And it's the smallest and most efficient solution on the market on this side. You can see the whole design is available from us, the design files you can get. So you can include all the schematic, all the layout into your PCB. This is just a demo here. You cannot buy this one, but you can, let's say, have for free the whole design to include in your system to get very close to your silicon carbide or the gallium nitride MOSFETs. The efficiency over the whole input voltage range is over 84%. The rail voltage regulation on the positive and negative are quite nice over the whole input voltage range and the whole power range. And as you can see, the whole solution takes only 14 by 27 millimeters. And for this kind of insulation and this kind of power, it's really unique on the market. There are no smaller solution at the moment. EMI is also not an issue if you take our, let's say, reference design. You can see here usually you don't need the conducted emissions test here, but we already did it. If there are some questions, The radiated is the more important one. You can see here the radiated charge in full power with long leads and no shielding. Usually the most designs are shielded, and the main issue are not the gate drive. The main issue is the power, let's say that the powertrain itself, the MOSFET and the switch power. So they are the main EMC issues usually. But to be sure, our device is not the issue. We made the test already for you, and the test is available if you need the reports. Of course, we made some thermal measurements, so the transformer can handle 135 degrees, and with full power, we reach at the snubber around 70 degrees. So there's enough headroom for designs with over 60 degrees of ambient at full power. You can use this design easily. Here you see some possible filter solutions for isolated power supply, because on the right side we have the power stage, on the left side we have the DC input voltage, and we have to protect the input from common mode currents from the high voltage side. And even if you got very small coupling capacity there, you have to make sure that the common mode currents are not feeding back to the input. So therefore, you can use with a dual supply this kind of, let's say, three-phase common mode choke. You always need a three phase if you have a dual output, because every return current must go through the same core to avoid saturation. And on the input, you can use a standard, let's say, two-phase common mode choke, which are pretty small and compact. You can see it here. These are standard products, and therefore, with this combination, you can get a really good EMI performance in immunity and in radiation. These are the curves for this kind of common mode chokes. You can see I used here very broad range products which cover let's say 100 kilohertz up to 300 megahertz. The same on the output side. So wideband products, broad range products will help you to pass EMI. So we already made some demonstrator here. You can see here the high side of our demonstrator, the upper leg. This is the SiC MOSFET. We have here a totem pole GaN FET, so we combine GaN with SiC. We have here the high-speed driver from TI. We have here the control PWM, and here we got the isolated gate drive supply. This is how it can look like. We switched up to 6 megahertz, so you can see these devices, the GaNs and the SiC, can go very high in frequency. And why did we choose this high frequency? Of course, to show the performance of the gate drive here, because the higher the switching frequency, the higher the gate drive currents will be, because they are multiplied by the frequency. And what are the challenges in designing something like this? Why do we choose GaN here in combination with SiC? It was simply to show how can we the gate as fast as possible charge and discharge the gate of the SiC. Therefore, we use the totem pole GaN, because these GaN devices can switch also very fast with this driver, and therefore we can sink and source very fast current to the SiC device. My colleague called it a machine of hell. It's not that easy to handle EMI with such high switching frequency. But this is not the issue here now. Just would like to show you what are the issues in layouting such systems with gate drive. You can see here is the flyback design. We have here the isolation barrier through the 4-layer PCB. And we have the isolation here from the control system. This is this isolator here, the eiSos 721. And we have here the basic insulation area, and between the outputs we have just a functional isolation, so we got no unwanted current between the high side and the low side. So this is usually how it's gonna done. The equipment and clearance, of course, depending on your design and your application, you have to handle here. And if you take a closer look at the gate drive, we have here the high-speed gate driver. We have the two GaN FETs from GaN systems. We chose them, and also the decoupling caps are very close to the GaN FETs. And then we go to the gate drive resistors, which are quite high, as you can see. They are pretty big because of the power loss of the high frequency and the high current here. And then we go directly to the SiC-FETs, which are on the low side for better cooling. And important is to get a very compact design in the end. From the common mode, this is the output of the flyback, the common mode choke here, and therefore we have the common mode ground, and this is always on one copper plane on the bottom side, which has a very compact, let's say, antenna or current loop. So we avoid any disturbance there. And as you can see, the GaN driver is quite close to the GaN FETs with 04, 02 resistors. So because this is even faster, this loop here, than the loop to the SiC MOSFETs, and therefore this has to be very compact in the end and as small as possible in area, so to avoid any direct, let's say, radiation there and any problems with common mode ground bounds. If you use SiC and GaN in applications, for example, one phase 4 kV, which is the maximum for one phase, then in the past it was mainly enough for many applications to use a manganese zinc common mode inductor with a X capacitor on the input filter. Maybe for more modern designs with gallium nitride and silicon carbide, as they switch mass faster, the frequency content in the, let's say, in the turn off and turn on slope is much higher. Therefore, you could maybe you're pretty sure you will need different kind of filtering at the input. So a good choice can be a combination of two different common mode inductors. So for example, a nanocrystalline or a manganese zinc for the lower frequency range up to maximum 30 megahertz. And for the higher frequency range, you can use this air gap inductor here. This is also a common mode choke with an air gap with a very high or very broad range in the higher frequency range. And as you can see, I made a very easy let's say common mode LT-SPICE simulation here. You can see from 100 kilohertz up to 100 megahertz, we got an attenuation with this kind of filtering here in combination with the Y capacitors. And of course, we also have to look on the differential mode with the same components. We made, I changed the LT-SPICE simulation to the differential mode. And therefore, we see also from 100 kilohertz to, let's say, 200 megahertz, we have a very broad range filter effect of combining a low and a high frequency filtering there for especially GaN or SiC applications. Yeah, why do we need often, or what's the purpose using GaN in low voltage DC-DC converters? There are some semiconductor companies which are pushing their, let's say, especially GaN devices, low voltage GaN devices under 100 volts to the markets. And what could be the benefit for you as a customer with this semiconductors? Well, as you heard already, or maybe you know, the switching speed or the edges of the switching is quite slow. So 1 nanosecond of edge is not a big issue with GaN. And therefore, we can drive DC-DC with very, very low duty cycles, lower than which is possible with standard lithium devices. So 1% of duty cycle is no issue with let's say, a proper GaN stage. And therefore, it's possible to directly convert down, for example, from 24 volt or 48 volt to 1.2 volt, as an example for a point of load DC-DC with very high current. So this could be an advantage. So we can skip one stage. Usually in the past, you have to convert from 24 to, let's say, 5 volt and from 5 volt to 1.2 volt. So we have two DC-DC converter stages, and the efficiency and the price and the layout, the space was then poor. And you can maybe skip this and only use one DC-DC stage. Maybe you are a little bit, let's say, confused why most of the reference designs of this high voltage GaNs or these low voltage GaNs are made with switching speeds under 1 megahertz, because they already proclaimed they can handle over, let's say, 10 or even 100 megahertz of switching speed. Of course they can, but then the efficiency is simply too poor. Yeah? So this is the reason why the most DC-DC low voltage GaN also working under 1 megahertz, because simply of the efficiency. They only cook with water, let's say. You cannot be above the physics. But to be honest, the real advantage is then to use them in application with low duty cycle then. And therefore, as the most GaN FETs and most drivers are pretty small in height and pretty small, you can also use them small polymer capacitors. then it's advantage to have an inductor with a very small height and low core losses under 1 megahertz and a very high current handling. So therefore, we developed a special package of the SiC-FET, as you can see here, where it can handle up to over 30 amps. The saturation current is here the limit, not the rated current, and with a very low DC resistance of 860 microohms. How you can choose this inductor, or you can select this inductor. Your Red Expert is your friend. It's a free simulation software for those who not know this so far. And you can make a simulation there. In this application, I made 84 volts to 1.3 volt, 20 amp, 500 kilohertz DC-DC stage. I put in the parameters in my window there. And then the program tells me how much inductance do you need. And if you choose then, for example, this 1 microhenry type here, what is the AC losses, the DC losses, and the total losses in your inductor, and how much. This is also very nice to know how much temperature rise can I expect in this application. And therefore, I can decide as a designer where 11 or 12 Kelvin temperature rise with these conditions. I can choose a smaller one because I can accept more heating. Or if I say, yeah, that's nice, then I can use the choke as a heatsink for the other components like the GaN FET. So you can suck out a little bit heat with your inductor then, because also it's a quite big copper structure there. You see the saturation current curves, you see the rated current curves here, and we are all within certain ranges. You can also put in here your ambient temperature, because manganese zinc and nickel zinc from the most inductors are influenced by the temperature. And if you put in a higher temperature here, the curve goes a little bit to the left side, and then you see if you already be in, let's say, in a safe zone where the inductance drops not too much. Okay, that's so far from my side. I'm ready for your questions.
Great. Thanks a lot, Andreas.
So let's see. The first question is, are there any advantage to use also for the low side transistor an isolated gate drive supply? Or when you should use an isolated for the low side device? Or when we should use an isolated for the low side device? Yeah, for the low side, that's right. It's not really 100% needed for a low side of a half bridge to use an isolated supply there. Depending really on your completely gate drive system, do you need an isolation there from the low voltage to the high voltage side? Usually, yes. And if you want to avoid any ground bounds, it could be also beneficial to completely, let's say, make a strict isolation between high side and low side. Then it's easier to control all the ground bounds in the system. So it costs more, it needs a little bit more space, but can help to get a more reliable and robust system. Hope it answers. Another thing. Where can I download the slides of your presentation? You will get from our marketing department after the sessions. You will get an email with a link for the download and also a link for the, let's say, recording of the video. So you can watch this video again and see the comments or hear my comments to the slides. But of course, you get also the PDF of the system, of the presentation, sorry. So we got another question regarding gate drive. Besides transformers topology, are there any other non-magnetic topologies such compared to such topologies? What are the benefits of the transformer topology? Let's say maybe there's a possibility to go with a capacitive system, but from a power density point of view and cost point of view, and let's say availability point of view, at the moment there's no real, so far as I know, maybe I'm wrong, alternative to a transformer-based system. Maybe what I can mention is there are a third topology proclaimed by TI in the last weeks or months. It's so-called LLC transformer for our auxiliary power supply. So we have an LLC system, not a flyback, not a push-pull, LLC system, which are which are also working with a fixed duty cycle. And this has the advantage. They told me it has a little bit lower EMI at a higher frequency range. And of course, as it's working with the stray inductance of these transformers, it's not sensitive to too high stray inductance of a transformer. So it's also beneficial. And then if you have a higher stray inductance, this means usually your transformer with the same construction has a lower coupling capacity. And therefore, we have the benefit of both. We have a lower coupling capacity, and you can use the stray inductance with the LLC topology. So you can choose between 3 topologies. All 3 are good. All 3 have advantages, disadvantages, let's say. Okay. So how does your losses calculation? Does your loss calculation for the choke, the real measurements? What? I have to make it a little bigger. How does your loss calculation for the chokes, the real measurements, what everything is included in the loss calculation simulation expert? So let's go back to the slide there. I think the audience means this one. What we did here is not only, let's say, a simple simulation. We really took some, let's say, 10 different pieces from 10 different let's say, manufacturing slots, and then we make the measurements with a special machine we got here. We made then, let's say, 10 different measurement points. The rest we interpolate between the measurement points. And this really not an estimation, it's really a measurement. So it fits very well. Of course, you have an influence of the inductor of the PCB where you solder this inductor and so on. But the results are pretty good. And at the moment, the best you can on more accurate you can get on the market, because we really made measurements for it and not only simulation. The problem nowadays with Steinmetz, as we did in the past, is that many modern or let's say latest inductors are working with different core materials and different kind of duty cycle, not only 50%, which is valid for the Steinmetz, not only sinus, which is only valid for Steinmetz. We are working with a rectangular voltage and so on. So the accuracy with the Steinmetz equations are not fitting quite well nowadays. Therefore, we really made measurements and put the results there in the Red Expert simulation system. So it's quite good. You're welcome. So another question, let me just read. Could you suggest a possible overcome the low side Miller capacitance coupling against high side dV to dt coupling in a half bridge? That's this phenomenon here we talk about. Let's just go back to the slide there. Or we know what we're talking about. Exactly the Miller effect, as I said. The problem here, we switch on accidentally, for example, the low side MOSFET due to the high dV to dt. Of course, we can. What you can do is selecting MOSFET with a lower Miller capacitance. Of course, that's the first point. Second point is, as I said, choose as possible lower negative voltage rail, not 0 volts. Choose maybe -4, -5 volts, depending on what your MOSFET can handle. And then you can control the speed of the edges. That means with the gate resistors, you can select, for example, if you use this combination here, you can select a different turn on speed and a different turn off speed. So this maybe also helps to handle this current. But much more will be difficult than, let's say, because there are not many other options in your system. So really turn off, turn on speed, and Miller capacitance as low as possible. And of course, a low clamping voltage for the gate turn off voltage. Okay.
Okay. Thanks a lot, Andreas. I would say because of the time, if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is from Mohamed Al-Alami with the title Better Safe Than Sorry, Practical EMC Design Considerations. So see you there in about 20 minutes, and goodbye.